All right, good morning. Welcome to perhaps one of the more depressing talks at the conference. But I hope there's some useful strategies for you to try to help find your way out of the mess that we're in. The web in particular as a platform has a lot of security implications in it because we're constantly interacting with new parties, new vendors. We're trying to buy stuff. We're trying to give our information, thinking in good faith, to other organizations. And there's just lots of opportunity for people to be fooled. Now, a talk like this could focus entirely on security features. I could talk about encryption. I could talk about authentication mechanisms. And that's one of the biggest misconceptions that people have, is that using security features means that you have a secure system. It's certainly part of the story, but it's not a sufficient part of the story. There's a lot more to it. So I want to start off talking about some of the engineering and other disciplines that we have in this space. And then once we're sort of predisposed to that, we will benefit from engaging security features like encryption and whatnot. So today we'll have a quick introduction. We'll talk about security engineering, largely influenced by a book by a guy named Ross Anderson. Part of your homework assignment. Highly encourage you read it. We'll have a section of ideas largely influenced by the work of Gary McGraw from a company called Cigital. Also part of your homework assignment. And then we'll look at some of the security controls that we have available to us on the web. How many people here are involved in security in some way? You can usually tell because they generally look like this, or if they don't, you know they're not really paying attention. Because absolutely every aspect of control or protection mechanism or infrastructure that we rely on is being attacked in some way or another almost on a daily basis. And it largely comes down to driving a wedge between the ideas of being trusted and being trustworthy. Right? So if we trust trustworthy people, everything's good. But if we have a way of driving a wedge between those concepts, then the trust that we give can be abused. So one of the first ways with the transitive trust model of the web, we trust our browsers, the browsers trust the certificate authorities, and in theory the certificate authorities derive trust for the people that pay them money to issue an identity certificate for them. But the problem is, if you can become a CA and you're not a trustworthy organization, then that's a dangerous precedent, right? So it's like hiring teenagers to run your movie theater. At some point, they're going to let their friends in the back door. So as a community, we sort of try to catch these things before they happen. And there are people, our organizations that have been thwarted from becoming trusted certificate authorities because collectively we said we're not convinced that you're not a front for the mob or foreign governments or whatever, terrorist organizations. So the next kind of attack is to take somebody who is trusted and attack them. So we have CAs like DigiNotar who had the hell hacked out of them a couple years ago, and we didn't even really notice, they didn't really notice, until there started to be a user in Iran who was hitting Gmail, and he started to notice really sporadic connectivity issues. And once he complained about this and raised the issue, people dug in deeper, and he was being sent a certificate signed as being by Google, but it wasn't by Google. And so people dug in deeper and realized that the attackers at DigiNotar successfully generated roughly 1,700 certificates as Microsoft, Google, a bunch of large name properties. And that's pretty much game over, because there's no way to distinguish between a certificate authority who is trusted, who's giving their trust, and one who has been compromised. And so very quickly after this happened, all the certificates from DigiNotar were ripped out of the major browser vendors because we could no longer trust them as a source. So we've got these various issues that kind of come into play, but it largely comes down to the users and their expectations and how they use the system. And if your website is complicated, if your application is putting a psychological burden on people, if they're easily thwarted by sort of interruptions from the side and social engineering attacks, then the privilege that you give your users as trusted agents in your system can become thwarted. And this is fundamentally why phishing is such an important part of the attacker's profile these days, is because we overprivilege our users, and they are the weakest link in most of the systems. So a combined effort where we reduce the privilege that we give our people to only that is sufficient to do what they need to do. We do not psychologically overburden them with complex interactions and tasks. And we train them on what to do, this is generally a strong strategy for improving the scenario that we're facing. Now the problem is every time that we say something, we say, hey, look for the locks. Then people start putting images of locks on their web page. We say, look at the URL, and then the URL becomes an attack vector, as we'll see in a little bit. And so, we've got the attacks that you've heard of at large sites with presumably sufficiently large budgets to manage security. But the problem is, nobody really wants to pay for security until it's too late, and then they'll pay whatever they need to. But the brand damage that goes with some of these compromises is probably worse than anything that they would have paid. Now, to some extent, the attitude has been like, well, I'll just hide in the crowd with everybody else who's being hacked. It's like, oh, okay, I've been hacked now too. I'm a member of the club. But things are different now, right? Particularly with the Target attack. The Target CEO lost his job because of this. And shareholders are not laughing anymore, right? This is not funny. This is not the tech people sort of, they don't know how to secure the system. This is real brand damage, and this is real value damage, and the shareholders are holding the executives accountable. And this is both good and bad news. I mean, the good news is I think the resources will be freed up. People will be willing to spend the money to invest the time to do this beforehand. The bad news is this is going to roll downhill, and this is going to be yet another thing that developers have to deal with. After we've also become testers and ops people and planners and everything else, we're going to have a hand in the security. Now, this doesn't mean every developer has to become a security expert. In general, organizations are going to need a software security group that is sort of like a tactical expert in this field that gets matrixed into the other teams to work with the developers to help mentor them in the security space. Generally now we have organizations set up to have development and then the security trolls, right? And everybody loves the developers and everybody hates the security trolls. And so there's really no incentive here to help the developers roll stuff out securely. And so there's generally an organizational restructuring that has to happen to commit to this as an approach, to build teams that know what they're doing, and to help have those teams help the other teams get stuff out. Because beyond the ones that you've heard about, if you go to hackmageddon.com, which is a totally cool place to go, I'm sure, we look through like this one block of attacks, and we see, in January we had this kind of attack on this person. It was this type of attack, this type of industry. We scroll through, and we realize, holy crap, this is only a 2-week period, and we have one of these for every 2 weeks for the last 4 or 5 years. This problem is out of control, and it's not getting better, it's getting worse. And particularly now that we're bringing devices into our homes, putting them on our networks, without segmenting our networks, without giving network restrictions so they can't see our computers and things like that, it's absolutely going to get worse. So we need to understand a set of approaches that work both at home and in our organizations, and it's generally about minimal privilege and not relying purely on perimeter controls. That's generally where people are these days. As of July of 2014, there had been almost as many attacks as the previous year, and it didn't slow down, and 2015 was no better, and 2016 is promising to be more the same. This Mandiant has put out this report that shows that the time from the earliest evidence of a compromise to the discovery of the compromise, now the evidence comes obviously before the discovery, is 205 days. Meaning people are getting into our systems almost 2/3 of a year before we discover them. And so the kind of damage that they can do, the kind of reconnaissance they can do, the intelligence gathering, setting up bots and backdoors and whatever it is that they want to do, that's a long time to allow them. And the longest presence that they detected was close to 10 years, which is unbelievable. Now, it doesn't help that our security people are generally working with the hackers. Not intentionally, of course, but they tell us to have passwords that are 8 characters long with these crazy combinations of uppercase and numbers and non-alphanumeric characters. And their intention is good. They just don't understand that they're fighting not yesterday's battle, not 5 years ago's battle, but maybe 20 years ago's battle. The idea of a dictionary attack was a thing 20 years ago. passwords themselves are just broken these days, if you don't know what you're doing. There's not enough entropy in an 8-character password like that to thwart people who can spin up GPU-based resources in the cloud to do direct attacks if you have crappy password strategies. And then the passwords that they're making us use are difficult to remember. And so basically, after 20 years, our strategy is to have passwords that are hard for humans to remember but are easy for computers to guess. And this is not a winning strategy, right? Choose a password you can't remember and don't write it down. So now we have entire teams that are set up to password resets, which just becomes another attack vector. And this is the thing. The controls we put in place tend to become new attack vectors because the people that are involved, the processes involved, the workflows that are involved are much easier to attack than cryptography or something else that we may have put in place. And so these become their way in. Now, this very famous XKCD cartoon got people thinking about this, but they didn't pay attention to every word there on the left. The position was, if we had a long collection of 4 random common words, then it's easy to remember, but there's a sufficient amount of entropy in the pool to allow it to be difficult to guess. People missed the word random, and they just said 4 common words. And so they started to pull words from poems and phrases and speeches and things like that, and there's nothing random about that. So hackers have started harvesting, the Gutenberg project and online speeches and song lyrics and things like that, and picking your common phrases from your favorite song, suddenly you're back to not enough entropy to thwart people. So we need to make sure that the controls that we're putting in place are explained well and enforceable. But the security community has also sort of responded to this cartoon by pointing out that making things easy for people to remember isn't really the goal. Having really hard passwords to guess is the goal. And so relying on password managers that have been vetted and proven, have gone through code audits and things like that is a better strategy. Because now you only have to remember one password and let the software do everything else until those are hacked because there are bugs in the implementations or something. As I said, you can now spin up GPU resources in the cloud. We've got people donating time on their computers to generate rainbow tables. And these are not necessarily malicious people. These are people who just want to highlight the fact that bad password strategies are a losing strategy in today's age, right? If you do not store your passwords with sufficient entropy and make it hard to guess, then you become susceptible to brute force attacks. Now, this was a problem several years ago when LinkedIn lost 6 million passwords. They had insufficient salting and hashing of their passwords. So within hours of this being reported, there was evidence of phishing attacks leveraging information from the attack being used by organized crime in Eastern Europe. Now, when the Ashley Madison attack happened recently, the security community looked at their database and said, okay, well, you've at least used bcrypt, right? This is a strong strategy because it allows you to slow down the calculation over time to respond to computers getting faster. But then they did something weird where they used the password :something else and an MD5 hash as part of a session. And once they were able to look at the code, then they were able to recover 11 million passwords of very unhappy people. So we have infrastructure. We tell people to look for locks. Websites put locks on the images. We tell people to make sure that the name is going to the right place. And so the name becomes an attack vector. If we have example.com ampersand gibberish equals 1234 at 167772161, I bet many people in this room would not successfully guess that that doesn't actually go to example.com. It goes to 10.0.0.1. So certainly our non-technical people that we're trying to get to make sure that the URL goes to the right place isn't going to go through and do the math. These 4 octets, when combined together, can be represented by the integer 167772161. Everything before the ampersand is considered username password. Now, the URL standard has been around for a long time, and it's not overly complicated, but for a long time, browsers implemented the parsing rules differently. So example.com/@coredump.cx would go to coredump.cx in Firefox. Example.com ;coredump.cx would go to coredump.cx in IE, it would be an error in Safari, and it would go to example.com in Firefox. The difference being, IE allowed a semicolon in the host name. So these different rules become ways of using the infrastructure and using the guidance that we tell people to lower their inhibitions by making them think they're making the right choice. Okay, I want to go to example.com, that's where I'm going, but maybe that's where you're going, and maybe it isn't. Then we have developers who think that they're too cool for school, right? When Tim Berners-Lee and Roy Fielding and the rest of our community say things like, do not abuse the idempotency and safety of the GET request, their answer is, you're not the boss of me, Roy Fielding. You can't tell me what to do. And then they write requests that do state change modifications with a GET request, right? As Tim Berners-Lee says here, the web is an information space. When you're browsing, you don't accidentally do things. Like, in this case, a transfer request was submitted for the following domains. Click on the following link to confirm the domain transfer request for these domains. We are trained to click on links in emails, which is why clicking on links in emails has become one of the biggest phishing attacks. And the problem is bad enough that the security departments of our banks say, do not click on links in emails. And then the marketing departments from banks say, hey, click here for a new offer, right? So within the organizations, there's not a consistent strategy around these things. And we have absolutely been conditioned to click on links. But what this does is this opens us up for things like cross-site request forgeries, where if I get you to open up an HTML attachment with an image reference that points to your broken API, and you happen to have cookies and things like that cached in your browser, then I can trigger you to do the bad thing I want you to do, because the browser is told from the time it's born, hey, GETs are safe and idempotent. It's okay to just go out and fetch images. We want you to. We want you to prefetch them so the user experience is better. So there are ways around this by using security tokens and things like that, but the point is, if developers just simply did not be so obstinate about what, how GETs work, then this would become less of an issue. So they counter by saying, well, I'm using role-based access control. And that's fine, except role-based access control doesn't generally scale as well as we would like. And one of the common problems in security is it doesn't matter if it's designed properly if it's implemented poorly. And during an audit of J2EE role-based access control systems a couple years ago, almost every single one had some way of thwarting it. Like they were only checking for the for verbs. They weren't checking for head. And head is just a GET that doesn't return anything. So if I can get a head request through, I've gotten a GET request through. Or they don't check, for verbs that don't actually exist but still trigger activity on the web server. So the point is, we need the approaches to combine together to give us strength in the complex, in the compound use of controls. If we constantly undermine the controls that we're trying to put in place, then there's no way that in practice they're going to be secure. So security engineering helps us understand why we're approaching these things this way, how much to spend. We generally don't want to spend too much, but we don't want to spend too little these days either. And so a good rule of thumb is to understand what value somebody would get out of hacking you and just make it not worth it. Sort of the too long didn't read summary of this talk is, if you make it a pain in the ass, they will probably go someplace else, right? There's generally like a 48-hour window I heard recently for most non-targeted attacks, where if you thwart them for that long, they're just going to give up and go someplace else. Now, if somebody's intent on attacking you, that's not going to be the case. But we do what we can against the attackers that we can. But this helps us understand roughly what our budgets should be. Enough to make it not worth it. Now, we generally think about what does it take to attack, to prevent attacks. But we have to design things to be safe against unintentional attacks as well. One of my favorite interview questions is, what's the worst bug you've ever written? And people laugh at themselves, and if they say they don't write any bugs, well, that ends the interview, right? Because you don't write software. But I know that people are nervous about admitting their faults, and so I always seed this with mine, which, because I didn't check the return value on a get-env environment request, I ended up destroying an RS-6000 workstation that we didn't have the installation media for. So my boss had to pack it up and drive it 2 hours to the customer site, reinstall the operating system, and bring it back. But I learned to check return values from get env requests, right? So the point is, there was a series of controls that had been undermined in that system unintentionally. We have to protect against both malicious attacks and idiots who don't check return values. And so we need to prove to ourselves that the system is resilient against certain kinds of attack. The problem is developers don't think like that. Developers are like, well, you told me to make it do this, and it does that, so I'm done. We have to think, oh, well, it shouldn't do this, so let's figure out whether it does or not. And so we need tests to prove that it doesn't do what it's not supposed to do, as well as that it does what it's supposed to do. Now, there's a common misconception that using encryption is a solution here. It may be a partial solution, assuming it hasn't been undermined by hackers, bugs, or national agents, which we'll talk about more tomorrow. But even so, encryption is about engendering secrecy. Secrecy may be a tool towards helping build security into your system, but it is an insufficient amount of effort to try to build security in. So you need to make sure that you're not confused that using security features is enough. You need to understand what the potential vulnerabilities are. You need to understand what the potential threats are. And those combined potentialities gives us a wide array of potential security breaches. Now, we don't necessarily want or have to address them all. But that's where having an understanding of the actual risks you're facing. Why will people attack you? What kind of people attack you? What value will they get out of attacking you? Where will they attack you? So using threat modeling tools and approaches will help us identify these things, generate a risk strategy, which then helps us prioritize the security approaches that we're going to take, as well as the feature rollouts that we need to sort of coincide with that. Because just like an infinitely scalable system that a startup spends 5 years building but has no users doesn't make any sense, a really, really heavily locked down system that has no features is also not of use. So security isn't in itself the goal. A successful, secure rollout of the features that you need to roll out is the goal. And so we need to balance how much time and money we spend on security protections versus actually building the system. A lot of systems will fail because we are protecting the wrong things. We don't understand that perimeter security and things like that are insufficient for our approaches, or we don't know where the real value are, or we're protecting the right things the wrong way, like by relying purely on perimeter security. Now, part of the problem, as I said, is there's a chasm between the security teams and the development teams in our organizations. The security teams have no real incentive except to keep their jobs. And they keep their jobs when bad things don't happen, so they just don't let anything happen. They just say no all the time, right? And that's not a winning strategy, right? That's a pure cost, and you don't even know necessarily that you're getting much value out of that because you're not actually rolling out features. So when there's an incentive mismatch, the people who make the policies don't have to live with the results. They don't suffer when things fail, generally, if they are sufficient. And if they just say no, 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 I said no, and your code still is broken, right? They can point the finger back at you and say, I didn't do anything wrong. You're the ones who had crappy code. Or they're just trying to cover their butts, right? They're trying to favor visible controls over effective controls. Now, I fly all the time. I am heavily incented to have a secure air travel situation. But I'm frustrated that we've spent over $15 billion on aggressive passenger screening as one of the primary forms of how we attempt to thwart the attack vector of September 11th. Now, in reality, that attack vector was closed within 6 months by securing cockpit doors, right? That was the major flaw in the system, and it's been addressed. The $15 billion plus that we've spent may have added marginal benefit, but not for the cost or the inconvenience that it puts us through. And by the way, it just builds everyone up into large lines at the front of the airport, which are easily attacked with a truck filled with explosives pulled up in front of the airport, right? So it's not that the point is to actually protect anyone or to avoid terror, it's to look like we're doing that. And that's a problem, right? We're favoring visible controls over effective controls. Now, we've had, since then, the shoe bomber, the underwear bomber, a couple other guys like this, they have not been thwarted by aggressive passenger screening. They have been thwarted by aggressive passengers, right? Hell no, we're not doing this again. So we need to understand what value we're getting out of the level of effort and money that we're spending. Now, I'm not saying don't not make people run through metal detectors and things like that, but let's find the right balance, because as somebody who flies all the time, this is a constant burden on me, and because of the profile that I have as a frequent flyer, my risk goes way, way, way down. I am unlikely to be an attack vector. I'm not saying it's unheard of that I'm an attack vector, it's just unlikely. So building a stronger risk-based profile, which is what TSA pre is supposed to be, but I'm finding that it's more and more just being given to everyone. And I guess it just means TSA pre 9/11, because that's back when security did what it did and we still kind of worked effectively. Now, to their credit, we don't know what the weakest link is in this kind of system. It's probably involving airport employees, right, who have access and don't go through the same kind of controls we do in many cases. But if we don't know what the weakest link is, it's hard to protect it. And if you're not protecting the weakest link, then everything else you're doing is probably not working either. The most prominent example of this was after World War I, the French said, wow, that sucked, let's not do that again. And they built the Maginot Line, an insanely well-engineered defense mechanism. Underground, these heavily armed turrets. There was indoor air conditioning to avoid gas attacks. There were long trains coming under mountains to avoid supply chain disruptions. And they fortified the hell out of their border with Germany, who then went through Belgium. And in hindsight, it seems obvious, right? But this is what we're doing in our environments. We're putting up firewalls. We're like, okay, well, the bad people are on the outside, the good people are on the inside, and that's going to be sufficient. But that is not sufficient. It may be part of the story, but when people bring their phones to work, and those phones get on the networks, or when people install Internet of Things devices on the networks at home, and they don't update them, then the TLS implementations and things like that they have in a year, in 2 years, in 5 years may become new attack vectors. So perimeter security is not enough, and we've got to stop pretending it is. We need to find and identify and address the weakest links, as many as we can. And we find these through risk modeling. We find these through threat modeling. We find these through thinking like an attacker, not like a developer. We then need a strategy so that the blocking of one or the thwarting of one control is caught by another. At a minimum, we can't have what happened at DigiNotar, which was they did not detect the attack until well after it happened. If you have a login API and you expect a certain number of logins per hour, then if 5, 10, 20, 100 times more logins happen in that period, then at least set off the damn alarm, right? Get somebody to look at it. So this involves plans, controls, operations, and development all working together with the testers, security testers, to make sure that the system has a compound collection of controls in place. Now, part of the problem is we have to roll out software now. We're trying to get stuff done today. And then the hackers have as much time as they want to address the problems. We have to find and fill as many holes as we can. They just have to find one. So the odds really are stacked against us. That's why we have to use our time, our money, and our effort efficiently and not waste it on controls that aren't actually going to solve the problem. So we have engineering protocols, we have security protocols, we have identity management systems, we have lots of ways of engineering these things in. But as software engineers building software using a controlled software process in most cases these days, we still want to know how do we get these efforts into what we're doing. And so Gary McGraw's Building Security In books from Addison Wesley, sort of the white hat, black hat books you've probably seen, are quite good ways of thinking about this. And he sums it up nicely in the comment that software security is not security software. Right? It's not something you buy. It's not something you install. Not saying these things are useless, they're just not enough. This has to actually involve the organization, their controls, their understanding of their risk, and the intentional combination of approaches in a deep strategy. So it's the idea of engineering systems that can continue to work in the face of malicious or unintentional attacks by idiots who don't check return values. Now, part of the problem is we have two main issues that we have to address: bugs and flaws, right? Bugs are crappy code, flaws are crappy design. Bugs are pretty easy to deal with, right? You issue a patch. You find them, you issue a patch, you can address those. The designs are harder. The design problems generally take, depending on the nature of the software, upwards of 4, 5, or 6 years to address. A flaw in the TLS implementation basically will take 6 years between the time it's discovered, a redesign happens, implementations happen, implementations are rolled out, and you finally get everybody off of old versions of IE. Then you can start to become more comfortable that this design flaw has been addressed. So empirically, based on studies, we see that roughly half of the problems that we face are bugs and half the problems we face are design flaws. So if we have strategies for addressing that first 50% relatively easily, relatively cost effectively, then that's a good thing to start with. So we have to have code reviews, static analysis, things that are part of your build process. When somebody checks the code in, if it's got a flaw, then we barf, right? And we complain, and we embarrass them just like we do when they check in code that doesn't compile or breaks tests. There's a feedback loop that happens there, right? Ooh, I guess I'm not going to do that again. Now we've got Find Bugs and Fortify and Secure Assist and a bunch of tools out there now that do this, but we're actually seeing companies like Codescope in Boston now starting to roll out tools that, as you're typing, as you're building, can start to do analysis and find code and have a learning process built into the development process. And it's exciting to see things like that roll out in this space as well. The problem is, if you don't address both, then that's not enough. So finding and fixing bugs, helping people learn from their mistakes and avoid them in the future, that's a good strategy for dealing with a big part of the problem. But the design problems are the harder ones to address. The design problems are the harder ones to detect. And so we'll need some strategies for dealing with that. So security is not sort of a binary state. It's not like you flip a switch or set a property in a property file and now your system's secure. Turning on TLS is not a way of turning on security. And even the whole notion of security is an ambiguous concept, right? To your company, it might mean, people can't do stuff with our resources that we don't want. To you as an employee, it might be, my company can't, monitor what I'm doing or what I'm saying in my emails, right? Security means different things to different people, but it's something that emerges if you put the right approach, design, controls, and things like that in place. It's not a guarantee, but it is how we make success. So the approach that works for most organizations is, number one, having a risk model. This is one of the biggest things people aren't doing now. They don't know why somebody would attack them in concrete terms. They don't understand how to use that to prioritize their spending on security. So having threat models, having approaches that help us understand these attacks and what somebody will get out of them is a good step to adopt. Gary calls these approaches applied to your software development process touch points. In our workflows, how do we start to adopt these approaches? And we'll talk about some of those in just a second. And finally, having people who know what they're doing is kind of a requirement. And this is the most maddening part, because competent engineers are hard enough to find. Competent engineers who also have a very good understanding of software and application development is almost impossible to find. And the problem is the security teams are largely staffed by sort of more network tool-oriented people, and they don't necessarily understand the software. And so they're giving controls and protections and things like that that are part of the story, but don't address the software side of things. And that's where things like a software security group are crucial. I'm using this one and this one. Page fault. All right. So Gary's approach doesn't involve any particular process, right? These are process agnostic approaches that deal more with the artifacts that are produced as part of our system. So we have requirements and use cases. We have architecture, design, test plans, code tests, and test results, and feedback from deployed systems. Right? So pretty much everybody building software will have some variant of these things. Now, the first, easiest, lowest hanging fruit that you can take control of is to have somebody who didn't build the system look at it, do a design review, because we have cognitive biases that if we miss things the first time, we'll probably miss them the second, third, fourth, fifth time as well. Now, this doesn't have to be an external security consulting company. It's just somebody within the organization who didn't build it. We'll take a look at it. And to start to collect feedback from the deployed systems, even if you're just going through beta, right? You need to learn how the system breathes. You need to know roughly under what circumstances do these things happen, how often do they happen, and build models that then feed back into your security requirements processes, so that you built in the ability to monitor APIs and do velocity checking. Now, you don't want to go, rigidly like, oh, we normally only have 1,000, so 1,001, I'm going to stop the system. You want to have some sort of statistical modeling and some cushion in there, but you do want to be able to detect abnormal activity on the system. That means having a secure logging strategy. And because part of the approach that we're addressing is to avoid internal threats, then logging things to systems that the admins of the apps don't have access to is a way of keeping them from covering their tracks by modifying the logs. But also because privilege escalation attacks are something we're trying to get away with, we don't want people to always have to do everything as root, because if they become compromised, then so do their privileges become compromised. So we want a secure logging strategy. We want an understanding of how the system breathes, and we want then that to start feeding back to our understanding of the production system. After that, it gets a little more complicated, right? We have abuse cases, security requirements, risk analysis, risk-based security tests, code review, risk analysis, pen testing, and security operations. Things like penetration testing are useful strategies to apply, assuming you understand how the system works, right? Just slamming packets against a solid wall isn't going to do anything interesting without an understanding of the doors and the pathways and how information flows through the system. Those factored into pen testing start to become a useful approach. So just using security software that you've installed isn't necessarily going to be the right starting point. Generally, the code review step is the right starting point. And this is not printing out some paper and pretending you read it on Friday when you go to a meeting for half an hour. This is static analysis as part of your build process, breaking when the expectations change. So you need to know what the expectations are. You need to know how to put controls in place to detect them. And that's where things like Secure Assist, Fortify, those sorts of tools have a whole set of categories of bugs that they're looking for. After that, everything is probably going to be driven by your risk analysis, right? So the second stage is to generate the risk analysis and use that to define the testing strategy, use that to do an architectural risk analysis to understand where there are issues in the architecture, and then that will drive the goals of things like the security testers in the pen testing approach to then find the holes in the system, at which point you can build security tests to say, yeah, this hole that's here, it shouldn't be here, we shouldn't do this. And then that feeds back into the development of abuse cases. Use cases show what the system should do, abuse cases show what the system shouldn't do, and then we build code that fulfill those abuse cases, and then the security tests pass. Just like the opposite way, where we're trying to prove that the system does what it is supposed to do with regular use cases and security tests. So this is not something you're going to do in the first iteration. This is not something you're going to do in the next 2 months. This is something that an organization collectively heads in the right direction, adopts these approaches, understands why they're adopting these approaches, adopts a risk-based strategy, and has people who know what they're doing who are appropriately incented to roll out software securely. Then you have a hope of having the security property emerge on your system. There's a lot to deal with, right? And it involves the whole organization. So a useful place to look for inspiration is the Building Security and Maturity Model. They've just finished the 6th version of this. It is a periodic survey of organizations, large, small, commercial, nonprofit, that have gone through this process or are going through this process and have identified controls that they've put in place and things. How do you handle with regulatory compliance? How do you deal with, do you have a software security group? These sorts of questions, and you can see some of the organizations that have been involved for a while and how they've changed over time. So if you go to bsimm.com, this is a comprehensive study. You can go and see how organizations like yours have addressed these things. With that in mind, we now have a process, a way of approaching and engaging security features in our system to help us thwart the kinds of attacks that we have. And on the web, that largely comes down to the valet key problem. Famously shown in the movie Ferris Bueller's Day Off, when they take the Ferrari, park it at the restaurant, go in for a while, or leave it at the valet parking, and the valet drivers go off on a joyride. This is what happens when you say, hey, I need your username and password, but once I have that, come on in, right? Do whatever you want now that you're inside, now that I know that you're one of us, right? We don't have authorization models that restrict our activities in most cases. I worked a couple years ago of doing some security consulting for how a large hospitality company used credit cards internally. And one of the things that we did was design a system with cryptographers that would generate a proxy, a cryptographically strong proxy for the credit card numbers, but it wasn't just a binary state, right? It wasn't just like, oh, it's protected, now it's not. We had 3 steps, and you didn't have to go through all the steps to get to the bank or to get to the last 4. So what this allowed us to do was to engender a new type of business privilege. People who worked at the front desk of their hotels never needed to see the whole credit card. They just needed to get to the last 4. And so that was the business privilege we would give them. People who worked in the marketing department who needed to make sure promotional points were associated with certain transactions needed to get to the bank, issuing bank of the credit card. So that was a privilege that we gave them. And only systems that actually needed the real credit card had the permission to get to that. So we need authorization models to restrict how even people that we do trust use the system and have it driven by business need and business risk, because that helps us with our defense in depth strategy. The principle of least privilege helps you thwart off large numbers of escalation attacks. So to do this successfully, we need to have a pretty good notion of identity. This means good account management. This means controls over the creation of accounts. Right? This should be a controlled, vetted process. Now, a lot of sites will just be like, hey, just give us an email address and we'll let you in. But if there is more privilege that's being afforded than that simple check, with a validation link that we send your email address, then somebody has to do this process, right? This is sort of acting in the role of the certificate authority. You can only create accounts if you're you can only have an account created if you're a new employee. So HR becomes the gate to somebody having an account created. That's not to say, admins can't create accounts, but then that should be a logged process, and that should be a securely logged process. So controls and management and an awareness of identity are part of the story. Managing that identity through things like good password policies and good password storage policies, using iterations to slow things down so that you have a way of thwarting brute force attacks on your hashing strategies, is all part of that story. Then having secure mechanism for authenticating these accounts and credentials that are being put in place, having an authorization model around what you're allowed to do, and not just at the perimeter. So something like OAuth is a reasonable strategy there, but within your applications, you should be doing checks at all levels. And then finally, the use of protected channels and secrecy to protect the tokens and things like that that are going back and forth starts to become a reasonable approach in this scenario. Generally, what we're trying to do is to build non-repudiation into our system. This is a business protection mechanism, right? When you go in and you buy wine at a restaurant, you get a chance to validate and verify the integrity of the request, and you get to even get a chance to taste it so that they have non-repudiation in the system. You cannot drink half the bottle and say, you know what, I don't really want this, right? That's a very expensive prospect for them. So the same thing on the web, like registering for things, ordering things, we want non-repudiation built into the system as well. Now the good news is the web interactions are client-server based. They're not decontextualized. Anybody can do anything to anyone via any protocol and any processing model and any technology like SOAP, which is pretty much impossible to protect. We have constraints on the interaction, and so we can, if we want to, verify who I'm talking to, assuming trust hasn't been compromised, and verify the clients, assuming their credentials haven't been compromised. But this becomes part of the interaction, and it's a simple model, and the channel itself can have protections on it so that we minimize the impact on the requests themselves. Now, that doesn't mean we don't want to do integrity checks on the requests. If we're passing through intermediate proxies and terminating at TLS at one point and then sort of reinitiating it someplace else, we want to make sure those don't become points of attacks as well. So we have the boundaries of the interactions pretty well defined. We just need to make sure we do the right thing as far as they're concerned. Now, the problem with security is it's never a free solution, right? There's always a cost, and there's always an impact. Having to always lock your doors or lock your car and whatnot becomes difficult. Like, oh, I got to get my keys out now, and I'm trying to carry something in the house. Security is generally annoying. So one case where we'd see this on the web is in the same origin policy. The goal here is to think, all right, well, if we're downloading arbitrary code off the web, then I kind of want to make sure that if you're hacked, that you don't send me attacks from somebody else. So generally, I as the browser, will not run anything that you give me unless it comes from the same scheme, host, and port. HTTP on this machine on this port. And so it's a reasonably good strategy. It's not foolproof, but it's reasonably good. It's also really annoying, right? Because while it may help protect us against attacks from others, it also helps us protect against ourselves. And that's where it starts to get annoying. If you're trying to build out an API and from api.company.com, but you're serving up content from someplace else, or you're using CDNs, or you're sharding your domain. I mean, there's a bunch of different ways this starts to become a pain. We want potentially a strategy for dealing with this. Now, people realized a while ago that browsers do not enforce the same origin policy on embedded HTML script elements. So if I have the ability to specify a source and I can tell it, here, generate some actual executable JavaScript which will get substituted in as the body of this element, then the browser will not enforce that. And I can return something that will invoke code in my browser. This is a hack, but it's a basically successful hack that people discovered. A more intelligently designed approach to this is called Common Origin Resource Sharing, and it's a collaboration between browsers and servers that support it. Servers that don't support it will basically stay the way they are, and the browser will not enable the request. But basically, the browser says to the server, hey, I'm asking for this, and I was sent here from this other server. Is that okay? And then the browser will say, yep, that's cool, I know that guy. And so we have the ability to control what requests are made via what methods, what request headers will we respond to, what response headers do we allow the client to see. And the browser acts as the guard. If the server says, no, you can't see these responses, then it strips them out before they're presented back to the client in XHR requests and things like that. So CORS is a fairly powerful strategy that's now pretty well supported in most modern browsers to give us the collaborative controls between browsers and servers to help avoid the same origin policy from protecting us from ourselves while still getting the protections that we want from bad people who want to break our systems. In terms of whether you can use JSONP or CORS, JSON-P works with older browsers, but it is also Git only. So again, these days, you should probably not have a problem using CORS just because of browser support, unless you have to support really old browsers, in which case, just quit. It's time to stop enabling these people. All right. Now, encryption is something that we can obviously effectively use. And you should make sure, I try to be specific and say you should use TLS. Even though occasionally I'll use SSL sort of indiscriminately to mean TLS, SSL is busted junk, right? If you're not following these kinds of attacks, if you don't know what crime and breach and beast and poodle and lucky 13 are, then I encourage you to dig deeper if it's your responsibility. Somebody in your organization needs to understand what these attacks are and how they are protected by design changes in TLS 1.2. And TLS 1.2 then is sort of the level at which you should, if you can, set the bar for your clients that you'll talk to. Understanding that not all old browsers support TLS 1.2, and therefore there may be a business impact on that choice. But you should at least be intentionally making that choice, not just sort of assuming that everything is just going to work. Deciding things like the cipher suites that you'll respond to are a key part of this. So yes, we get encryption out of this, we can identify parties out of this, but the reason that it continues to work as computers get faster and new attacks on designs come in is because we control the conversation. We can say, I will not talk to people who are using busted hashes or old, insecure stream ciphers, right? I want to use advanced encryption with authentication, with extra additional authentication data. I want to be able to use sufficiently large keys. I want to use only hashing algorithms that have not been known to be broken. That is controlled through the cipher suite selection. So other than that, we can manage certificates. We can do integrity checks using HMACs and shared hashing keys and things like that. And this is where it becomes an effective tool to at least help us understand who we're talking to and whether our attack or our communication has been intercepted and manipulated. One of the important things, like the Poodle attack, leverages flaws in SSL 3, so we need to make sure that we are protected against downgrades. You know, if the browser starts off and says, "Hey, do you speak TLS 1.2?" "Yeah, I do," and then some kind of attack says, "But let's just speak plain text anyway," right? That's the kind of thing you want to make sure doesn't happen, and that the session should be terminated if anybody tries to. So our basic approach to authentication in this space is to say, "Hey, can I have that?" And the server will say, "Nope," unless you say please. So the www authenticate basic is a way of saying, look, unless you change how you're asking this, I'm going to keep saying no, but I'm going to give you a hint. Right? If you know how to talk to me this way, then things might work in your favor. So the browser knows how to do this, and so it collects a username and password from the user and submits an authorization header, issues the request again, and the server says, hey, well, why didn't you say so? And it works even if you just send the authorization in the first place. If you know that a server is using HTTP basic, you can send it in the first place. You don't have to have the round-trip approach. The problem is, if you're not using TLS, then what is actually sent is a base 64 encoding of username password. And for the record, Scott and Tiger are terrible username and passwords. At least Tiger. Scott may be okay. The problem with base 64 is it's a reversible process. There's no key involved. And so anybody who comes across the packets can figure out what your username and password are. And so that's where tools like Firesheep, which is a plugin for Firefox, allows somebody to sit in Starbucks and listen to your network traffic. And they can reassemble it and get your username and password for Facebook or Twitter or Flickr or whatever. So what? You can get to my social media account. Why is that a problem? You may be an idiot and use the same password everywhere. Yes, that's one part of the problem. What else? These sites are how we learn where you grew up and what street you grew up on and what your mother's maiden name is and whether you have a dog and what your dog's name is, right? These security questions are generally terrible and easily thwarted by the use of social media. So if somebody can intercept the traffic, they can generally gain leverage to attack you in new ways. Now, basic authentication over TLS, that's a different story, right? It doesn't help solve the valet key problem, but at least it's understood. We understand how to attack it. We understand how to protect it. So it's at least a simple approach. So the take-home message is not use HTTP basic. The take-home message is if you use HTTP basic, at least use TLS, right? Because then the attacker has a much harder time recovering the username and password. We thought digest would be a good solution to this problem. The idea is we're not actually sending the password. And this cannot be done in one step. This has to have a round trip because the server has to give the client a nonce to avoid replay attacks. So here, you are given a choice. Do you want a quality of protection of auth or auth int? And depending on the choices you make, you're going to send back different hashes and hashes of hashes and things that avoid replay attacks but don't require TLS, and yet still securely send the credentials over the wire. Not the credentials, but the hashed result of these things over the wire. So the idea is your client asks for it, it's told no, it says, here's how you say please. Saying please in digest is much more complicated. Pick your quality protection, here's the nonce and an opaque key to send back, regenerate things, send the state back, because this is a stateless interaction. The server's not remembering, hey, what did I send you? And then it's going to say, all right, this user with this password generated this hash with this nonce. I come to the same answer with what I have on my end. Yeah, okay. It's probably this person, or at least they stole that person's credentials. Now, this is an interesting idea, but it hasn't really gone anywhere. It's widely supported, just not widely used, in part because TLS over BASIC does roughly the same thing. And now there's a push to do TLS everywhere, which kind of eliminates the need for something that doesn't work, doesn't require TLS. So digest, everyone uses, has the ability to use it, they just don't. One of the interesting things about TLS everywhere, though, is that it now is driving phones and devices like that don't have hardware accelerated support for crypto primitives. Generally, a lot of the Android devices don't. So they're using the CPU more, which means now that everybody's using encryption in more places, your battery life sucks. So Google's working on developing some cipher suites that are efficient on general purpose computation devices and secure, that will help address this kind of issue. So again, security is a pain in the butt, right? It's hard not to have negative consequences to adopting these sorts of things. All right, so OpenID was an idea that identity management is hard to get right. And if you're a coffee shop that wants to sell coffee to people, you don't really care about having a strong account management system. If you're selling sandwiches to somebody, you don't really care who it is as long as you sell sandwiches, right? So they give you a little card, and after 7 sandwiches, you come back and get your 8th one free. They don't care that it's you, or you could take the first one and hand it off, and you're the one who gets the free sandwich. And if you do this every single day, you're happy, and everyone else is like, what the hell, where's my free sandwich? They don't care, right? They just want to sell sandwiches. So the idea here is if you don't really care about having control of the identity, you just want to be able to associate transactions with an identity, then outsourcing identity to something like an OpenID provider makes sense. Unfortunately, it didn't really take off, in part because it assumed a web redirect interaction. So before, people had phones and devices and native applications communicating on the web more readily. That doesn't work as well here. Asking people to remember their URL instead of a username and password was kind of a drag from a user experience perspective. So the idea of just pure identity management has kind of fallen away, but we're seeing it reborn as things like OpenID Connect. So associating identity management with an authorization model like OAuth helps strengthen the offering of an identity service. And so we're starting to see things like that as well. So OAuth 1 was an attempt by a lot of companies in Silicon Valley to put an authorization model on the web, to allow somebody to give somebody else permission to do something in a distributed and loosely coupled way. So the canonical example is you take a fancy picture, you put it up on Flickr, people are stealing people's Flickr pictures and putting them on like political ads and things like that. So you don't let the high quality one be seen by anybody. You have a watermarked version that you let people see. But if you decide that you want to print out your own high quality picture through some kind of printing service, then we need to coordinate the authorization grant from the resource owner, you, the client, the printing service, and the resource server, like Flickr. So you go to the printing service and you say, hey, print that picture. They say to Flickr, hey, can I have that picture? Flickr says, hey, go ask him. Can I get this picture? Yes? Okay, then away you go. So in that sense, we're delegating to me the ability to delegate to them the ability to access my resources, but it's only my resource. They can't print other pictures. They can't remove things. So generally on Twitter, to say I can read your timeline, but I can't tweet as you. Those sorts of controls we want to put in place. I built a commerce API for a large consumer electronics retailer, and one of the first users of it were credit card companies who wanted to convert points into purchases, and they were never proxying this retailer's accounts. They were always proxying their own credit card users' accounts. So we did not give those credit card companies the ability to create new accounts, because as the business relationship stood, there was no reason to allow them to do that. And it wasn't that we didn't trust them, because who doesn't trust credit card companies? It was because if they got hacked, then they could become part of a privilege escalation. So we just simply said, no, we do not give you that privilege, therefore we don't have to worry about their credentials being hacked in that way. Some of the other goals of OAuth 1.0 were to create, to not require TLS. So we have this complicated signing strategies around the requests and the responses. The spec wasn't overly well written, wasn't overly well implemented, and there were bugs. And we could no longer just use HTTP. We had to use an OAuth client that was written against a poorly written spec, and that became kind of an issue. So collectively we said, all right, this is a neat idea, but it's too complicated for the simple case of, hey, let me see your crap on Twitter. Hey, let me see your pictures on Flickr. And so OAuth 2 was an attempt to have a simplified version that was easier to use, easier to implement, and used things like bearer tokens. So we did still have the ability through extensions to do some of the complicated signing stuff, but we also had this new idea of a bearer token that I could just hand over in exchange for access to something. So we can associate state with the bearer token, or attributes with the bearer token, and it's like money, right? Anybody will accept money for an exchange of services. But just like money, if you steal my cash, you can use it. If you steal my bearer token, you can use it. So we have to have the ability to have expirations on these things and control access to them. We also require the use of TLS, because if you're handing this around and this is like cash, then we don't want to leave cash in our logs and things like that. It's also important to do certificate chain validation. This is one of the things that most people don't do. So and a lot of hackers will leverage that fact. By attacking somebody and generating a fake certificate, we check the certificate, but not the chain back to where a root of trust. Now, part of the problem is even with this approach, we have to be able to control, respond to attacks. So in this case, this service, Best Parking, had their credentials hacked, which meant somebody was able to tweet as them. So sorry for the spam, be careful about giving posting permissions, because if those apps get hacked, you do too. This is the thing to remember. Principle of least privilege does not necessarily mean I don't trust you as an employee. It means I want to reduce your chance of being part of a privilege escalation. And people generally respond more positively to that kind of approach than, I don't trust you, dude. So there's usually a registration process with the OAuth 2 approach. So requests are tied to a particular client, a particular app, and that way if you get attacked, I can then say, nope, no more app for you, and everyone else can continue on happily. You're generally given a client ID and a secret, and you use these to exchange tokens for authorization access tokens for authorization tokens, and that way I know they're falling in the right hands. You also can register a redirect URI. So if you send the client, the resource owner to me, and then we do the grant access, then I know where to send them back. And I'll use some combination of query parameters, headers, fragment identifiers, or something to give you your access token. So Jacob Yenkov has a bunch of great tutorials online. I stole his images just because they're cute and better than I would have done. So he's got a series of roles here in the OAuth 2 space. He's got a resource owner, that's us. We've got the client application, that's Flickr. We've got the resource server, the client application is the printing company. The resource server is Flickr. And then the authorization server may also be Flickr, or it may be a separate authorization. There's two roles that may be played by the same party. So in this case, you do a request. Preferably, we return the bearer token over TLS as a response header. Why do we do that? Why is it preferred to that? Yeah, generally access logs would have things like this in it, and we want to avoid that. So if you can use the headers, that's a preferred approach, but we can't necessarily force clients that don't know how to use it to use headers, so we may have to just give them a URL that has the token in it. So at least make sure you're doing that over TLS. So one of the things OAuth 2 does is to expand the number of client profiles. We have a server-side web app that is acting on our behalf, but is not actually exposing the user to the credentials. So that's a fairly secure mechanism. Our interactions with the credit card company were like this. They were never handing over the bearer tokens to the clients. They were just acting on their behalf on the back end. Sometimes we'll run the app actually in the client-side's browser, which expands the attack space. So we're going to treat that as a different security profile. We have native applications, so a desktop application. We don't want to invent a new authorization model just for a different type of client. So we want to be able to support these kinds of clients as well. So on the server-side web app, our browser is sent an application by the web server, but the interactions are all mediated by the server on the back end. And so this is a relatively strong profile. In this case, we do the grant access. Hey, can this thing see your picture? Yes. Then it gets returned through the redirect URI, and generally the authorization code is a parameter that's going to be stripped off. The server exchanges this for an access token with its client credentials, so I know that the right token for this transaction is being handed to the right user. So we're getting some defense in our compound controls here. And this allows us to do things like refresh tokens to say, you can log in for a couple weeks, right? So you don't have to constantly be logging in. So we'll give extra leeway to clients like this because the surface attack area is smaller. Now, in this case, the app runs on the client's browser. Now I have to worry about whether you're running IE7 or something like that, right? My attack vector goes up much wider. So in this case, I'm going to operate slightly differently. You're given the grant access, but I'll return the access token via a fragment identifier. I'm not going to do a client credential exchange. You're just going to strip off the access token and use that for subsequent requests. And that's how I'm going to identify you there. Because of the higher attack space, then I'm not generally going to support refresh tokens in this space. Right? So this is the difference between something that you'd log into, and as soon 10 minutes later of inactivity, I'm going to kill your token, versus a business relationship between two partners that can last for weeks or months at a time. And the reason is because the user agent has access to this. So a hacked browser or poorly implemented browser has some exposure for these credentials. As I said, the native application, we can exchange username and password for a token and then use that as part of the request. Generally, you only want to do this if it's a trusted client because they might do something stupid like get the credentials and then write them to the disk, which is the equivalent of locking the front door and putting the key under the mat, which is something people do more often than you would want to think. So this is another strategy. In this case, you just exchange the username and password, and you only have to have the password to establish the token, and then you can use the token for as long as the session allows before you have to prompt again. All right, the final one is a client credential grant authorization for maybe Internet of Things devices or things that you don't have a lot of control over, you can't necessarily deploy software to. It's not an overly safe approach, but it's a simple approach where you have some kind of prearranged shared key, and I just exchange that for the token. This is not the preferred use, but to support sort of limited capability clients, it's in there as well. So we call this sort of the two-legged flow. All this is great as long as everything else works, and everything else doesn't always work. I'll talk about this more in the encryption talk tomorrow, but 2014 was a pretty bad year. Every major implementation that we rely on had a 0-day associated with their secrecy management stuff called TLS or SSL. And the problem is, if that's broken, the control that you're relying on is broken, then I can steal your tokens and do what I want. We've got complex systems. So here, this guy named Igor Homakov was demonstrating how they hacked the OAuth 2 system in Facebook by leveraging bugs in Chrome. And again, we're seeing combinations of design flaws and implementation flaws undermining. Even if OAuth 2 isn't perfect, under certain circumstances, it can have reasonable protection capabilities unless you're running on flawed software. So the future, I think, is more promising. Not in the immediate future, but over time, we've got new identity management stuff coming out with ties to authorization models. So OpenID and UMA are things to look at. We've got the W3C working on capabilities for strong cryptographic primitives in the browser, including access to things like hardware security modules, things like the YubiKey. So this is something that you plug in, your key is on that device, it's never taken off of that device, and therefore there's a lower attack probability of somebody just stealing your key off of your hard drive or something. It's got to be plugged in, and there are protections against it coming off the key. It's not, it's not impossible, but it's much less likely. So good adoption of the W3C web cryptography working group, I think, will help. There are things, I'm involved with something called the Web Credentials Initiative. It's not a standards track yet. We're trying to get it to be supported. But this is a way of exchanging privacy-preserving, portable, machine-processable credentials that allow you to make verifiable claims in simple and varied ways. So when you go to a gas station and try to buy cigarettes or alcohol, you hand over your driver's license, which is a credential that people trust, because it's hard to forge, but you're also saying, by the way, here's my name and my home address as well, right? And somebody who's able to memorize that, you're leaking too much information. So in this case, I could do something like issue a proof of age credential for the current user that's digitally signed by the DMV without actually exposing your username or home address. So things like that we're trying to do, and yet at the same time not tie you to a permanent identity like your Facebook account or an email address. You can take your credentials with you as you accumulate classes and courses and certifications and things like that, and store it at whatever identity provider you want. Finally, we're having HTTP signatures, signing HTTP messages, ways of protecting messages in transit. So lots of these sorts of things are coming. So your homework assignment. Gary's books are great, sort of cross-platform, cross-language thinking about designing software in a secure way. As part of his series, this book, Enterprise Software Security, helps identify the problems most organizations have structurally with respect to security and how to sort of realign these initiatives with the development efforts. Ross Anderson's Security Engineering, I cannot recommend enough. It's a lot of generalized principles up front and then vertical slices, like what does this have to do for the banking industry or nuclear power management or other kinds of verticals. Excellent, excellent book. Adam Shostock's Threat Modeling represents Microsoft's view on threat modeling. There are other views, but this is a pretty widely accepted view for companies with the sufficient resources to put it in play. Maybe difficult for smaller companies to expend that kind of effort, but definitely worth your time to look into. Michael Zalewski's The Tangled Web is a good modern book on the approach. Talks about cross-site request forgery and other kinds of attacks like that. I encourage you to take a look at. Cores in Action is the most comprehensive walkthrough of implementing cores and what it's good for and how to use it I've seen. Ryan Boyd's OAuth 2 is a tiny little book, but it introduces the terms and the basic approaches for OAuth 2. Bruce Schneier's Applied Cryptography Bible is sort of a modern distillation of thinking on this. It just came out with its 20th anniversary, updated for recent events. Cryptography Engineering and Practical Cryptography are other books by him that may be more directly applicable for day-to-day use. But I think the single most important book, if you're doing web security stuff, is Ivan Reichstick's Bulletproof SSL and TLS. It's very accessible. It's not overly theoretical. He keeps the digital version up to date. So if you buy the digital version, he'll send you updates with rewrites as new attacks come, and sort of, it's another attack like this. And he's got a really cool newsletter where he'll summarize when new attacks come out. So this is something that I think most developers should have access to. So thank you very much for your time. I hope you found it useful. It's hard to hope that you enjoyed it because it's kind of depressing. But we're getting better at building these systems, but it's going to take combined effort of your organization, the developers, the testing team, and everybody else. So thank you very much, and I hope you enjoy the rest of your day.